Hello friends, let's continue with quantization. In this lecture, we will look at non-uniform quantization. What is the motivation for non-uniform quantization? Let us recall that in uniform quantization, the step size, that is the gap between two successive quantization levels, delta, is fixed. This constant delta leads to the quantization noise power delta square by 12, which remains fixed. And because the noise power is fixed and the signal power, depending on the message signal, keeps varying, we end up with a variable signal to quantization noise ratio or variable SQNR for fixed delta. Normally, with practical signals, what happens is that the amplitude of the signal keeps changing, as in speech signal, for which it mostly occupies low amplitude regions, and only occasionally the voltage level or amplitude level is high. Indeed, in voice signals, the highest to lowest voltage ratio, depending on the loudness, can be as high as 1000. And this large difference between the signal amplitude with time results in a significant variation in the signal power. And if we still have a constant step size, fixed noise power, the signal to noise power ratio will be changing drastically over time, and this is something undesirable. What we actually need is that when the signal occupies low amplitude regions, the instantaneous power will be low, and therefore there the noise power should also be low. And lower noise power can be achieved by keeping delta small, the step size small. And when the amplitude of the signal is higher, the signal power is higher, and therefore we can tolerate larger step size and therefore larger noise power. So the idea is that uniform quantization leads to a constant noise power, which further leads to a variable SQNR, signal to quantization noise ratio. But our objective is to achieve almost constant signal to quantization noise ratio, and for that, if the signal power is varying, the noise power should also vary, and noise power can vary by changing the step size depending on the signal amplitude. So the solution is to have variable noise power, and that can be obtained by having variable step size so as to achieve fixed or almost fixed SQNR. So when the message M has lower amplitude, there we need smaller step size. We need finer resolution, so a smaller step size, and a smaller step size will lead to low noise power and therefore high SQNR. And when the amplitude takes larger values in the higher amplitude region, we can have higher step size delta, which will have higher noise power, but because the signal power is also higher, we end up getting an acceptable SQNR. So uniform quantization, fixed delta leads to poor SNR at low amplitudes, whereas non-uniform quantization, in which we make our step size delta variable, it leads to almost fixed SNR at all amplitudes. That is what is desired. So how to achieve such a non-uniform quantization? One of the ways to achieve non-uniform quantization is to first compress the message signal, and then the output of the compressor should be uniformly quantized. Let us understand it this way. Suppose we show the normalized output and normalized input here. So the characteristic of our compressor is like this. So you can see that if you look at the lower amplitude region, the lower amplitude region gets mapped to a higher output levels. A kind of expansion is there. But if we look at the higher amplitude part, so you can see that the higher amplitude region of the input gets mapped to a smaller amplitude range. So basically we get a compression here. So it is with respect to this higher amplitude region for which we get compression that these characteristics are called compressor characteristic. And once we have converted these variable amplitude regions into the compressor output. And now if we go for uniform quantization, we have actually achieved in effect non-uniform quantization with respect to the original input levels. So at the transmitter, we compress the higher amplitude part of the input signals. At the receiver, we need to do the opposite of it, which we call the expansion characteristic. So at the receiver, the characteristic would be like this. So if this denotes the characteristic at transmitter, at receiver will have to have the complementary characteristic. So if we are doing compression at transmitter side, we have to do expansion at the receiver side, and these two operations together, compression plus expansion, leads to what is known as companding. So non-uniform quantization is implemented through a compander in a communication system. Practically, these compression characteristics are achieved by what are called compression laws. There are two laws prevalent. They are known as mu law and A law. The mu law characteristic is shown here for various values of mu. This is the empirical expression that is used to achieve the compression characteristic. Here we have taken the magnitude of the input signal in a normalized way. So it occupies from 0 to 1 range. Actually, it is from -1 to 1, but because we have taken the magnitude, it is from 0 to 1. Similarly, we are taking the magnitude of the normalized output. So as just explained, the compression characteristic is concave. If mu is 0, there is no compression. If mu takes on getting positive values, we get compression. It has been found that for mu equal to 255, we get such a compression which leads to almost constant SQNR over a wide amplitude range. So this is the typical value used wherever mu law is used to achieve companding, and that is the case for US and Japan. A similar characteristic, a similar law is known as A law, whereas the parameter is A instead of mu, and this is the expression to implement it. The characteristics are similar, concave characteristic as we see, and here the typical value of the parameter A is 87.6. So whether it is mu law with mu equal to 255 or A law with A equal to 87.6, both of them give almost similar behavior with almost constant SQNR over a wide amplitude range. Mu law characteristics are implemented in US and Japan, whereas A law is used in Europe and most of other countries. The main advantage of companding or non-uniform quantization for that matter is to achieve almost constant SQNR over a wide amplitude range of the input signal and to achieve effective channel utilization by keeping the bit rate in check. So that's all for this lecture. Thank you very much.